So here's example 2 where we're going to be looking at some of our special pattern um, binomials to factor. Now, if you haven't already watched the 4.4 special patterns video, you're going to want to go back and review that. These are two binomials that fit those patterns, the difference of cubes and sum of cubes. Just to remind you guys what they look like, if we go back here, we've got the sum of cubes and difference of cubes. So we have this special pattern that these types of binomials fit. So in here, you're just going to see an example of two binomials that fit this pattern and how we can go ahead and factor these problems according to this pattern. So again, if you haven't watched the special pattern video yet, go watch that and come back to this one. So in part A, we've got x cubed minus 125. Like I said in the previous, the special pattern video, when you're identifying the sum and difference of cubes, some of the perfect cubes should jump out at you and help you identify these. The fact that it's two terms, so a binomial, and the fact that we've got a variable to the third power and a term that is a perfect cube. 125 is just 5 to the third power. So the first step is rewriting this so we can identify our a and b terms. Now, when we rewrite that, we identify that our first term is just our a term is x, because we've got x to the third power. And like I said, 125 is just 5 to the third power. So here we've got x is our a value and 5 is our b value. Now all this is just plugging in a and b for that pattern, for that formula for the difference of cubes. So again, this is just something you should memorize when you identify this. It's just like the quadratic formula. You memorize this and just plug your a and b values in accordingly. So when we plug a and b, or x and 5 in for a and b, we get x minus 5. Then we get x squared plus 5x plus 25. So if we go back and look, our difference of cubes is just a to the a minus b times a squared plus ab plus b squared. Here we've got a minus b times a squared plus ab plus b squared. Notice since b is 5, we get 5 squared, which gives us 25. Okay, very straightforward. There's not a whole lot of explanation. It's just being able to recognize these perfect cubes and then plugging the a and b values into this pattern. Now, the second, it takes a little bit more work, because right looking at it, you don't see 16 and 54 aren't perfect cubes. We've got s to the 5th power and s squared, so you don't see a third degree right from the start. But if you recall, our first step is always factoring out any common factors that ours has. So if you look at these, obviously you see that they both have the variable s. And here we've got 5 s's, and here we have 2. So that means we can factor out s squared from both of these. Also, when you look at your coefficients, we've got 16 and 54. Now, when you go ahead and start looking at factor pairs, you're going to realize that 2 is the largest factor that you can take out. So 2s squared is the largest factor that we can take out. And when we pull that out, we're left with 8s cubed plus 27. Now, this should look more like the perfect cubes that we've been talking about. You'll see that s to the 3rd power is a variable cubed, and the coefficient 8 and our constant 27 are both perfect cubes. 8 is just 2 to the 3rd power, and 27 is just 3 to the 3rd power. So what this is going to look like, when we rewrite this, we're actually going to get this is 2s to the 3rd power plus 27 is just 3 to the third power. So what we get here when we are looking at our patterns, we get that our A value is just 2s and our B value is just 3. So when we go to look at our pattern here, we're going to see that A is 2s and B is 3. So I'm going to go back and show you guys once again this pattern so we can see we've got A cubed plus B cubed. We're just going to plug our A and B values into here. So let's go back to the problem. Now that we know A is 2s and B is 3, I do want to point out, since, and I mentioned this in the special patterns video, but here, since we have an A value that is not just a variable, remember, we are squaring our entire A value. So this is not just going to be 2s squared. That's a common mistake people made. We're actually taking our whole A value, which is 2s, and we're going to be squaring that for this first part of our second polynomial. So as I click back and we go through that, just keep in mind that for this first term here, A squared, we do not write it as 2s squared. It is the quantity of 2s to the second power, which is going to give us 4s squared. So let's go back and go through this. So remember, our 2s squared has to stay out in front. When we plug in our A and B values here that we get 2s and 3, we go ahead and get 2s squared times 2s plus 3, just our A plus B. And then, like I mentioned, A squared, which is just 2s to the second power, we get minus AB, which is just 2s times 3, and then we get plus B squared, which is just 3 to the second power. So I went over special patterns in the previous video, and now we've done two examples of sum and difference of cubes. One, which is very straightforward, you just see a variable cubed and a perfect cube, and another where you actually have to pull out a greatest common factor before your binomial looks like a difference of cubes. So at first glance, this doesn't look like a special case, but when you go through and pull out a greatest common factor, you do get it to look like a difference of cubes.